All right, let's dive straight in. We're here to talk about the future of the vehicle, specifically its nervous system, the communication architecture. This isn't just a technical overview, it's a strategic report designed for the engineering leaders, for you, the people who are actually building the next generation of software-defined vehicles. So let's start with the big thesis right up front. The communication technology in a car, it's not just a data pipe anymore, not by a long shot. It's become the cornerstone, the foundation upon which a vehicle's value, its features, and, most critically, its safety are built. It's everything. Okay, here's how we're going to break this down. We'll start with the why, the strategic inflection point we're at. Then we'll get into the what, the next-gen architecture itself, covering the backbone, the bridging layer, and the edge. And we'll wrap up with the how, a concrete strategy and execution roadmap. All right, section 1, the strategic inflection point. Let's really dig into why we're having this conversation in the first place. We're standing on what you could call a burning platform. The way we've been building in-vehicle networks for the past couple of decades, well, it's just not going to work anymore. It's totally unsustainable. And here's why. Look at this number, 50 gigabits per second. Just let that sink in for a moment. That's the bandwidth we're going to need in a single vehicle in the very near future. That is a 20 times increase from where we are today. This isn't some minor evolution. It's a revolution, and it's being driven by an absolute tidal wave of sensor data. But, and this is the really critical part, it's not just about more speed. It's actually convergence of three major forces, all hitting us at the same time. First, you've got this data explosion from all the sensors. Second, you have the non-negotiable demands of L3 and L4 autonomous systems for determinism and safety. And third, well, we're hitting a wall with physics. The traditional copper cabling we've relied on is simply running out of steam. It's too heavy, too noisy, and it just can't handle these new speeds. Okay, so we've defined the problem. Now let's move on to the solution. What we're proposing is a comprehensive, future-proof architecture for the vehicle's nervous system. We've broken it down into a clean, three-tiered MECE framework, where each layer has a very distinct and vital purpose. So let's look at these three layers. You've got the backbone for high-speed transport, the bridge for deterministic connectivity, and the edge for reducing complexity. And yeah, we're using a MECE approach here. That's mutually exclusive, collectively exhaustive. It's a fancy way of saying that each piece has its own job, and together they cover absolutely everything, from the multi-gigabit core right out to the tiniest sensor at the edge. No gaps, no overlaps, just a clean, logical design. Okay, let's start with that first layer, the high-speed backbone. This is the superhighway of the car's network. And when you're dealing with high-voltage EV environments, we have to face facts. Copper is reaching the end of the road. It's time to make a strategic choice. So let's put them head to head. Copper versus optical fiber. Copper, as you know, is a magnet for electromagnetic interference. The signal dies off pretty quick, and it's heavy because of all the shielding. Optical fiber, on the other hand, it's completely immune to EMI. It can go for 40 meters or more with almost no loss, and it's ridiculously light and thin. The big takeaway here? That EMI immunity is a game changer for EV platforms. It dramatically simplifies your design and validation, which saves you a ton of time and money. But the strategic advantages go even deeper. First, it's standardized under IEEE, so there's a clear roadmap. Second, the latency is incredibly low, less than a microsecond, which is exactly what you need for safety-critical systems. And third, and this might be the most important point, it's future-proof. You lay that fiber once. Just once, and you can upgrade from 10 gigs to 25 to 50 just by swapping out the electronics at either end. Your capital investment is protected. All right, on to our second layer, the deterministic bridging layer. This is what connects your zonal controllers to the central compute. Think of it as the series of bridges that connect the superhighway to the local roads. And on these bridges, we need two things: a good amount of bandwidth and absolute clockwork-like predictability. And this is where CAN-XL comes in. Look, CAN is probably the most trusted, most battle-hardened protocol in automotive history. CAN-XL isn't throwing that away. It's evolving it. It's the perfect technology to bridge that critical gap between legacy CAN and the super high-cost, high-speed Ethernet world. And when you look at the technical evolution here, the numbers are pretty impressive. But the one that really matters, the one that changes everything, is the max payload. We're going from 64 bytes in CAN FD all the way up to 2048 bytes. That's a huge leap. Why does it matter? Because with a payload that big, you can now tunnel entire Ethernet frames. And that's where the commercial value really kicks in. This ability to do Ethernet tunneling means you can support modern service-oriented architectures and push faster over-the-air updates, all while reusing the existing inexpensive twisted pair wiring that's already in the car. For migrating to zonal architectures, this is a massive, massive win. Now, on top of all this, we layer time-sensitive networking, or TSN. You can think of TSN as the metronome of the entire network. It provides that sub-microsecond clock synchronization, and, crucially, it guarantees transmission slots for critical data. It ensures that your most important, safety-critical messages always get through. On time, every time. No excuses, no matter how busy the network gets. Okay, that brings us to our third and final layer, the wireless edge. Now, out here at the periphery of the network, our strategy changes a bit. The goal isn't necessarily more speed. It's about reducing complexity and, most importantly, reducing weight by getting rid of physical wires wherever we possibly can. And the technology of choice here is automotive-grade Bluetooth Low Energy, or BLE. We're already seeing the first silicon hit the market, like the Renesas chip mentioned here. This opens up a ton of applications. You can revolutionize TPMS, making it a two-way system. You can replace entire chunks of the wiring harness for things like ambient lighting or door locks. And because it's ultra-low power, it's perfect for sensors that run on batteries. The key takeaway is simple. We're trading copper for silicon to reduce weight and simplify manufacturing. Okay, so we have the architecture, but as we all know, a strategy is only as good as its execution. So in this final section, let's get down to brass tacks. Let's talk about the very real challenges of implementation and how we can tackle them head-on. First up, migration. This is a tough one. You've got these legacy CAN nodes, and they see a new CAN XL frame. They don't understand it, they think it's an error, and they can basically shut down the entire bus. So what's the countermeasure? It's a strategy we call node classification. You have to be disciplined. You identify which nodes are legacy, which are capable, and you use bridges to physically isolate the old ones so they can't cause trouble. Next up is validation. The software complexity in these new systems has just exploded. We're talking a 100-fold increase. You can't wait around for silicon to be ready before you start your software validation. It's just too late. The solution is to shift left. You have to move your testing into the cloud. By using virtual ECUs, you can validate maybe 80% of your entire communication stack before you even have a single piece of hardware in your hands. And finally, security. In this new world of connected high-voltage vehicles, security is not a feature you add on at the end. It's not a checkbox. It has to be designed in from the very beginning. That means mandating hardware security modules, HSMs, at the chip level. It means deploying layered security at the protocol level, things like MACsec and CSOC. This is table stakes. It's absolutely non-negotiable. So to wrap this all up, here are 4 concrete strategic recommendations, 4 actions for your roadmap. First, standardize your interfaces. Lock in on IEEE 802.3z and CAN XL to protect your investments. Second, embrace the optical backbone. For any new premium platform after 2026, it should be the default choice. Third, automate your tool chains. Move away from manual work and towards model-based automated pipelines. And fourth, build a more flexible supply chain. Demand more from your suppliers and move towards pre-integrated platforms. Look, what we're talking about here is a reboot moment for automotive communication. It's a fundamental turning point. The architectural decisions you make today, right now, are going to define your vehicle's capabilities and your company's competitiveness for the next decade and beyond. The only question left is your architecture ready for it?